Hello and welcome to Science for Bedtime. This is a place where science can move slowly without pressure or urgency, and where curiosity does not need to stay alert to be present. The ideas you'll hear tonight don't need to be remembered or followed closely. They can simply pass by one after another like distant lights seen through a window. If these quiet science stories have found a place in your evenings, you're welcome to support the channel by liking the video or subscribing. It helps this space continue to exist gently and consistently for anyone who might be looking for it. The solar system is often pictured as a neat diagram, planets arranged in careful order around a glowing center. In reality, it is a slow conversation between gravity and motion unfolding over billions of years. Nothing here is in a hurry. Each world follows a path shaped long ago, and those paths continue whether they are noticed or not. At the center of it all is the Sun, containing nearly all the mass of the solar system. Because of this overwhelming weight, everything else responds to it. Planets settle into stable orbits. Smaller bodies drift but remain bound. Even distant objects feel its pull. The Sun does not chase its companions. Its gravity is simply there, steady and unavoidable, guiding the entire system into a shared rhythm. Deep within the Sun, energy is created through nuclear fusion. In its core, hydrogen atoms are pressed together so tightly that they combine to form helium, releasing energy in the process. This energy takes an unimaginably long time to move outward through dense layers before finally escaping as sunlight. When it does, it spreads calmly in all directions, warming planets, shaping atmospheres, and illuminating worlds that never come close. Closest to the Sun is Mercury, a planet that does not hold onto a thick atmosphere. Instead, it has a delicate exosphere so thin that particles rarely collide. Atoms are lifted from the surface by sunlight and tiny impacts, drifting briefly before many of them escape into space. Mercury's outer envelope is always changing, never fully settled, a faint presence rather than a protective shell. Even so, Mercury still hides something unexpected. Near its poles are deep craters that sunlight never reaches. Inside these permanent shadows, temperatures remain low enough for water ice to persist. On a planet known for extremes, intense heat and sharp cold exist side by side, separated only by the angle of light and the depth of stone. Moving outward, Venus turns in a direction opposite to most other planets. Its rotation is slow and reversed, causing the Sun to rise and set in unfamiliar ways across its cloud-covered sky. The reason for this unusual spin is still uncertain, possibly linked to ancient collisions or long-term atmospheric effects. Venus rotates as it does without explanation yet complete, holding on to a mystery that has lasted for billions of years. Venus is also the hottest planet in the solar system, even hotter than Mercury. Its dense atmosphere traps heat with extraordinary efficiency, allowing warmth to build and remain near the surface. Sunlight enters, but energy struggles to escape. The result is a planet where distance from the Sun matters less than the way air itself holds on, turning Venus into a world defined by retained heat. Farther out, Earth follows a different pattern. Its surface is divided into large plates that slowly move over time, driven by heat from within. These shifting plates build mountains, open oceans, and recycle material between the surface and the deep interior. The motion is measured in centimeters per year, almost imperceptible, yet over long spans it reshapes the entire planet again and again. Earth also hosts water in a rare balance. Ice, liquid oceans, and water vapor all exist together on its surface and in its atmosphere. These forms move between one another in a continuous cycle, responding to temperature and pressure rather than remaining fixed. Water here is never truly still. It flows, freezes, evaporates, and returns, creating a quiet stability that supports long-lasting change. Above Earth, the Moon slowly drifts farther away each year. This gradual movement is caused by tidal interactions, a gentle exchange of energy between Earth's rotation and the Moon's orbit. The change is small, but it accumulates over time, altering tides and reshaping the future of eclipses. The Moon's path is not permanent. It is slowly, patiently adjusting. Mars carries clear traces of a more dramatic past. Rising from its surface is Olympus Mons, the largest volcano known in the solar system. It grew to such a scale because Mars lacks moving tectonic plates, allowing eruptions to build upon the same location for immense periods of time. Today, the volcano stands silent, its size speaking for processes that once reshaped the planet from within. Beyond Mars, Jupiter dominates its region with mass and motion. Within its vast atmosphere spins the Great Red Spot, a storm that has persisted for centuries. The Great Red Spot changes and shifts, yet it remains, a reminder that on some worlds, even weather can become enduring. Encircling Saturn are its famous rings, composed mostly of water ice. Each ring is made of countless individual fragments, all orbiting together in a thin, flat plane. From a distance, they appear solid, but they are held together only by gravity and motion. Light reflects from their icy surfaces, giving them their brightness, while their structure remains delicate and constantly in balance. Between Mars and Jupiter lies the asteroid belt, where Ceres stands apart. Large enough to be classified as a dwarf planet, Ceres has a rounded shape and signs of a complex internal history. It is not simply debris left behind. It is a small world that formed early and endured, carrying clues about the conditions that shaped the young solar system. Nearby, Vesta tells a different story. It is differentiated, meaning it once had enough internal heat to separate into layers, forming a core and mantle. This places it somewhere between a simple asteroid and a fully formed planet. Vesta is a preserved fragment of planetary construction, a body that began the process but never completed it. Taken together, these worlds follow the same quiet rules. Gravity gathers matter, heat moves energy, light travels outward, and cold waits patiently where warmth fades. Nothing here demands attention to continue. The solar system remains steady in its slow motion, carrying on with or without observation, content to exist exactly as it is. Beyond the region of the main asteroid belt, the solar system opens into wider spaces where gravity still rules, but distance begins to soften its grip. Jupiter is not only massive, it also possesses the strongest planetary magnetic field known, extending far into space and shaping an enormous magnetosphere. Charged particles become trapped within it, forming radiation belts that glow invisibly and influence the environment around the planet. This magnetic presence is so vast that it would appear larger than the Sun if it could be seen directly, a quiet but dominant structure shaped by motion deep within Jupiter's interior. Jupiter also radiates more energy than it receives from the Sun. This excess heat comes from the planet's slow gravitational contraction and leftover warmth from its formation. The energy rises from within and drives powerful atmospheric currents, fueling storms and cloud bands that never fully settle. Jupiter is not cooling quickly. It is still releasing echoes of its own birth long after the surrounding space has grown calm. Orbiting Jupiter is Io, the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions, driven not by internal radioactive heat alone, but by tidal forces. As Io moves through Jupiter's intense gravity, it is stretched and squeezed, generating frictional heat inside. Lava flows and towering plumes rise again and again, leaving little time for impact craters to accumulate. Io's landscape is renewed so often that it rarely keeps a memory of the past. Nearby, Europa presents a quieter face. Beneath its cracked and streaked ice shell lies strong evidence for a global subsurface ocean of liquid water. Tidal heating from Jupiter flexes Europa's interior, preventing that ocean from freezing solid. The surface shows long fractures and disrupted regions where ice has shifted and refrozen. Europa is cold and dark, yet beneath the ice, water may slowly move, hidden and persistent. Farther out, Ganymede stands apart as the largest moon in the solar system. It is even larger than the planet Mercury. Ganymede is also unique among moons because it has its own intrinsic magnetic field. This field creates auroras within its thin atmosphere and suggests a complex, layered interior. Beneath its icy surface, scientists suspect multiple layers of ocean separated by different phases of ice, stacked quietly deep below. Callisto, another of Jupiter's large moons, appears heavily cratered and ancient at the surface. Yet measurements hint at the possibility of a subsurface ocean beneath its outer shell. Unlike Europa or Ganymede, Callisto shows little surface activity, preserving a record of impacts from the early solar system. If an ocean exists there, it is deeply buried, isolated and calm, sealed beneath ice that has not shifted for eons. Moving outward again, Saturn reveals a different kind of balance. Despite its enormous size, Saturn has an average density low enough that it would float in water if such a scale were possible. Its bulk is spread through layers of hydrogen and helium, giving it a lightness relative to its volume. Rapid rotation causes Saturn to bulge at the equator and flatten at the poles, shaping it into a softly compressed sphere. Saturn's rings are not permanent features on cosmic timescales. Observations suggest they are slowly losing material as ice particles spiral inward under gravity and electromagnetic effects. Over very long periods, the rings thin and fade, with fragments falling into the planet's atmosphere. The rings appear timeless when viewed briefly, yet they are part of an ongoing cycle of formation and loss. Among Saturn's many moons, Titan stands out for its thick atmosphere. It is the only moon in the solar system with a dense, nitrogen-rich atmosphere that supports complex weather. Clouds form, winds blow, and rain falls, but the rain is made of liquid methane and ethane rather than water. Rivers and lakes carve Titan's surface, following patterns that feel familiar, even though the chemistry is entirely different. Beneath Titan's icy crust, evidence points to a subsurface ocean of liquid water mixed with ammonia. The thick ice above acts as insulation, keeping the ocean from freezing solid. Titan's surface chemistry, combined with its hidden ocean, makes it a world of layered processes, where surface weather and deep interior conditions coexist without ever meeting directly. Closer to Saturn, Enceladus is small but unexpectedly active. Jets of water vapor and ice erupt from fractures near its south pole, spraying material into space. These plumes originate from a subsurface ocean kept warm by tidal heating. The expelled material contains salts and organic compounds, indicating interaction between water and rock below. Enceladus quietly feeds Saturn's E-ring, linking moon and planet through a continuous exchange. Uranus follows an entirely different rhythm. Its axis is tilted by about 98 degrees, causing the planet to rotate on its side. As it orbits the Sun, one pole faces sunlight for decades, while the other remains in darkness. This extreme tilt creates long, unusual seasons that unfold slowly, each lasting many years. Uranus does not simply spin. It rolls along its path, carrying its rings and moons with it. Uranus also possesses a faint ring system, darker and narrower than Saturn's. These rings are composed of ice and rocky material and are aligned with the planet's tilted equator. From certain perspectives, they appear almost vertical, tracing thin lines through space. Small moons help maintain their structure, shaping gaps and edges through subtle gravitational interactions. Neptune, the outermost major planet, appears calm from afar, yet it hosts the fastest winds observed in the solar system. These winds race through its atmosphere at extraordinary speeds, driven by internal heat rather than sunlight alone. Neptune radiates more energy than it receives, and that excess power fuels dynamic storms that form and fade against a deep blue backdrop. Triton, Neptune's largest moon, orbits in the opposite direction of the planet's rotation. This retrograde orbit suggests that Triton was captured rather than forming alongside Neptune. The capture likely disrupted Neptune's original moon system and generated internal heat within Triton itself. Even now, Triton shows signs of geological activity, with icy geysers venting nitrogen into space. Beyond Neptune lies the Kuiper Belt, a broad region populated by icy bodies left over from planetary formation. Pluto is one of the most well-known members of this distant zone. Its orbit is highly elongated, and for part of its long year, Pluto travels closer to the Sun than Neptune. Despite this crossing, the two never collide, held in a stable orbital resonance that keeps their paths separated in time. Pluto's surface hosts vast plains of nitrogen ice that flows slowly like glaciers. These frozen fields can reshape terrain over long periods, smoothing impact scars and forming subtle patterns. Beneath the surface, Pluto may harbor a subsurface ocean, kept warm by radioactive decay within its interior, insulated by layers of ice above. Pluto's atmosphere is thin and temporary. As it moves closer to the Sun, surface ices sublimate into gas, forming a fragile envelope. When it drifts farther away, the atmosphere freezes and falls back onto the surface. Pluto breathes in this slow, seasonal way, its atmosphere appearing and disappearing across its long orbit. Far beyond the Kuiper Belt, a distant reservoir of icy objects is thought to exist, known as the Oort Cloud. It is not a disk, but a vast spherical shell surrounding the solar system. This region is believed to be the source of long-period comets that arrive unexpectedly from all directions. These objects spend most of their time in deep darkness, only briefly visiting the inner regions before returning outward. Comets develop tails when they approach the Sun, but those tails always point away from it. Solar radiation and the solar wind push gas and dust outward, creating luminous streams that trace invisible forces. The direction of motion does not matter. The Sun's influence shapes the tail, turning each comet into a visible marker of energy flowing through space. The Sun's influence extends outward as a bubble known as the heliosphere. Formed by the solar wind, this region shields the planets from some interstellar radiation. At its boundary, the pressure from the surrounding galaxy begins to dominate, marking a transition rather than a sharp edge. Space does not end there, it simply changes character. The solar system itself is not stationary. It moves through the Milky Way, orbiting the galactic center over hundreds of millions of years. During that long journey, it passes through different regions of interstellar space, each with its own density and conditions. Even as planets trace their familiar paths, the entire system drifts onward, carried quietly through a larger cosmic pattern. As the solar system continues outward, its smaller inhabitants begin to tell stories just as complex as the planets themselves. Many asteroids are not solid slabs of rock, but loose collections of fragments held together by gravity. A gentle disturbance could change their shape, reminding us that not everything in orbit is firm or permanent. Some bodies endure by strength, others by quiet cohesion. A few asteroids even carry their own moons. These tiny companions circle their parent bodies in miniature orbits, bound by gravity on a scale that is easy to overlook. Their existence shows that even small objects can form systems of their own, repeating the same physical rules that guide planets and stars, only in softer, slower motion. Meteorites that fall to Earth sometimes come from Mars. Powerful impacts on the Martian surface can eject rocks with enough speed to escape the planet's gravity. Over long periods, a fraction of this material crosses interplanetary space and eventually reaches Earth. These stones carry chemical signatures that match measurements taken on Mars itself, offering natural samples delivered without spacecraft. Earth's magnetic field is generated deep within its interior by the motion of molten iron in the outer core. This moving metal creates a protective magnetic shield that deflects charged particles from the Sun. Without it, Earth's atmosphere would be far more vulnerable to erosion. The field is invisible, yet it quietly guards the planet, shaping auroras and preserving conditions near the surface. Auroras form when charged particles guided by Earth's magnetic field collide with gases in the upper atmosphere. Oxygen and nitrogen respond by emitting light, painting the sky with soft greens, reds and purples near the poles. These displays shift and ripple in silence, visible reminders of the Sun's ongoing interaction with Earth. The Sun itself undergoes cycles of magnetic activity. About every 11 years, the number of sunspots rises and falls, reflecting changes in the Sun's magnetic field. During more active periods, solar flares and eruptions become more frequent. The cycle is not perfectly regular, but it provides a slow pulse to solar behavior, expanding and contracting like a quiet breath. Sunspots are regions where strong magnetic fields suppress the flow of heat from below, making them cooler than their surroundings. They appear dark by contrast, not because they lack energy. Some sunspots grow larger than Earth itself, forming and dissolving over days or weeks, surface features that reveal hidden forces beneath the Sun's glowing skin. Solar flares release bursts of energy when magnetic field lines suddenly realign. These events send radiation and particles outward through the solar system. When directed toward Earth, they can disturb satellites and communication systems, though the planet's magnetic field absorbs much of their impact. The Sun is steady overall, but not entirely calm. Light from the Sun takes a little over 8 minutes to reach Earth. When sunlight touches the ground or warms the air, it has already completed a long journey through space. What is seen is not the Sun as it is in that instant, but as it was moments before. Even in everyday brightness, there is a small distance in time. Mercury's orbit played a role in confirming Einstein's theory of general relativity. Tiny shifts in the planet's closest approach to the Sun could not be fully explained by classical physics. Relativity accounted for the discrepancy by describing how mass bends space itself. A small planet moving close to a massive star helped reveal a deeper structure of reality. Venus has no natural moons. Despite being similar in size to Earth, it orbits the Sun alone. The reason remains uncertain. Possible explanations include past collisions or orbital dynamics that prevent stable satellites. Venus moves through space without a nearby companion, its sky empty of a familiar secondary presence. Mars experiences seasons, much like Earth, because its axis is tilted at a similar angle. As Mars travels around the Sun, different hemispheres receive varying amounts of sunlight. These seasonal changes affect polar ice caps, atmospheric pressure, and dust activity. Though colder and thinner in air, Mars follows a recognizable rhythm of light and shadow. Mars is also known for global dust storms that can envelop the entire planet. Fine particles are lifted by winds and can remain suspended for weeks or months, blocking sunlight. These storms reshape surface features and influence temperatures, creating a world where even air made of dust can dominate the sky. The Moon is unusually large compared to Earth, especially among the planets. This relationship likely resulted from a massive collision early in Earth's history, after which debris gathered into the Moon. The pairing has remained stable, shaping tides and influencing Earth's long-term balance. The Moon experiences quakes. These moonquakes are caused by tidal forces, temperature changes, and impacts. Some last much longer than earthquakes on Earth, reverberating through the Moon's rigid interior. Though the Moon appears still, it is not entirely silent within. Jupiter is known to have the largest number of confirmed moons, Many are small and irregular, likely captured objects. Others are larger and more complex. Together, they form a diverse system shaped by Jupiter's immense gravity, a miniature reflection of planetary variety. Some of Jupiter's smaller moons orbit in unusual paths, including retrograde or highly inclined orbits. These patterns suggest capture rather than formation in place. Jupiter's gravity acts as a collector, gathering objects that pass close enough to be retained. Saturn's moon system is equally intricate. Some moons act as shepherds, guiding ring particles into narrow bands and sharp edges. Their gravitational influence maintains the structure of the rings, preventing them from spreading evenly into space. The moons and rings exist in constant interaction, shaping one another through motion. Enceladus quietly feeds Saturn's E-ring. Ice grains and vapor expelled from its surface escape the moon's gravity and settle into orbit around the planet. The ring system is not isolated. It is fed, altered, and renewed by its nearby companions. Titan's thick atmosphere contains complex organic molecules formed by sunlight interacting with methane and nitrogen. These compounds drift downward, settling onto the surface like a slow chemical rain. Titan's environment shows how rich chemistry can develop even far from the warmth of the Sun. Uranus has an unusual magnetic field that is tilted and offset from the planet's center. As Uranus rotates, this creates a constantly changing magnetic environment. The field does not align neatly with the planet's spin, producing complex interactions with the solar wind. Neptune's deep blue color comes from methane in its atmosphere, which absorbs red light and reflects blue wavelengths. Beneath this calm appearance, storms rise and fade, driven by internal heat. Neptune's surface is not visible, only the top of an ever-moving atmosphere. Neptune has a faint ring system composed of dark material. Unlike Saturn's bright rings, these are subtle and difficult to observe. Their existence shows that rings are not unique to one planet, but can form under varied conditions. Many Kuiper Belt objects have highly inclined or elongated orbits. These paths preserve clues about early gravitational interactions among the giant planets. The outer solar system still carries the imprint of ancient migrations. The Oort Cloud, if it exists as theorized, may be the most distant reservoirs of objects still loosely bound to the Sun. Objects there are only loosely bound, easily disturbed by passing stars or galactic tides. Their orbits are long and slow, stretching time itself. Voyager 1 has crossed the boundary of the heliosphere into interstellar space. Its instruments measure changes in particle density and magnetic fields, offering direct data from beyond the Sun's immediate influence. The spacecraft continues onward, carrying a record of Earth with it. Voyager 2 has also entered interstellar space, following a different path. Together, the two probes provide multiple perspectives on the boundary between solar and galactic space. Their signals arrive faintly, reminders of journeys that do not end quickly. The heliosphere changes shape as the solar system moves through interstellar clouds. Pressure from surrounding material compresses and stretches it over time. The Sun's protective bubble is not fixed. It responds to the environment beyond. The solar system formed from a collapsing cloud of gas and dust about 4.5 billion years ago. As material gathered at the center to form the Sun, the remaining disk flattened and cooled, allowing planets to assemble. The structure seen today reflects that early rotation. Rocky planets formed closer to the Sun, where heat drove away lighter elements. Gas giants formed farther out, where colder temperatures allowed hydrogen and helium to accumulate. Distance determined composition, setting worlds on different developmental paths. Planetary orbits are elliptical rather than perfectly circular. Each planet has a closest and farthest point from the Sun, affecting speed and received energy. These variations are small for most planets, yet they are always present, subtle departures from idealized shapes. The solar system's planets orbit roughly in the same plane, a remnant of the flattened disk from which they formed. This shared alignment reflects a common origin, rather than coincidence. The system remembers its beginning through geometry. Even now, the solar system continues to change. Orbits shift slightly, atmospheres evolve, and surfaces respond to slow processes. Nothing here is completely finished. Motion continues, quietly and persistently, across scales of time that do not need to be measured to be felt. Even the smallest details of motion leave long traces over time. Mercury, for instance, has an unusually large metallic core compared to its overall size. This dense interior makes up most of the planet's volume and contributes to its weak but measurable magnetic field. How Mercury came to be so metal-rich remains uncertain, with ideas ranging from ancient impacts to early formation near the Sun. What remains clear is that its interior tells a story very different from its modest appearance. Mercury also experiences extreme temperature differences between day and night. Without a thick atmosphere to distribute heat, its surface can become intensely hot under direct sunlight and plunge to deep cold in darkness. These swings are among the most dramatic in the solar system, shaped simply by exposure and absence rather than weather or wind. The Sun itself has layers that behave in unexpected ways. Above its visible surface lies the corona, an extended outer atmosphere that reaches temperatures far hotter than the surface below. This inversion of heat has puzzled scientists for decades. Magnetic activity and wave-like motions are thought to transfer energy upward, keeping the corona intensely hot even as it thins into space. To better understand this region, the Parker Solar Probe travels closer to the Sun than any spacecraft before it. Protected by a heat shield, it passes through the outer atmosphere, directly sampling particles and magnetic fields. Its measurements help reveal how solar wind forms and how energy moves through the Sun's atmosphere. The probe does not linger. It passes through, gathers data, and continues on its looping path. The solar wind itself is a steady stream of charged particles flowing outward from the Sun. It carries magnetic fields with it, filling the heliosphere and interacting with planets along the way. This flow shapes comet tails, compresses planetary magnetospheres, and defines the boundary where solar influence fades into interstellar space. Mars once had flowing liquid water on its surface. Evidence remains in the form of dried river valleys, sedimentary layers, and mineral deposits that form only in the presence of water. The planet's atmosphere is now thin, but its rocks preserve signs of a wetter past, when conditions may have been more hospitable. Mars also has two small moons, Phobos and Deimos, which are irregular in shape. They resemble captured asteroids more than typical moons, though their exact origin is still debated. Phobos is slowly spiraling inward toward Mars, destined either to break apart into a ring or impact the surface in the distant future. Deimos, meanwhile, drifts slowly outward. Earth shares its orbital neighborhood with small objects known as co-orbital asteroids. These bodies follow stable paths that keep them near Earth's orbit without becoming moons. Some trace looping or horseshoe-shaped patterns, guided by gravitational balance rather than direct attachment. They are quiet companions, present but rarely noticed. The asteroid belt itself is mostly empty space. Despite popular imagery, the distance between individual asteroids is vast. A spacecraft can pass through without encountering any obstacle. The belt's total mass is only a small fraction of Earth's moon, spread thinly across a wide region. Some asteroids spin rapidly enough to change shape. As rotation speeds increase, loose material can shift or even escape, altering the asteroid's form. Over time, this can create elongated shapes or binary systems where material separates and enters orbit. Binary asteroids consist of two bodies orbiting each other. These systems provide insight into how gravity works on small scales. Their mutual motion reveals mass and density in ways that single objects cannot, offering quiet lessons in balance and attraction. Jupiter's interior pressure is so great that hydrogen behaves like a metal. In this metallic hydrogen layer, electrical currents generate the planet's powerful magnetic field. This state of matter does not exist naturally on Earth, yet it is common inside giant planets, shaped by gravity alone. Jupiter's magnetosphere captures particles ejected from Io's volcanoes. Sulfur and oxygen ions become trapped, forming a torus of material around the planet. Io and Jupiter are linked through this exchange, connected by invisible flows of charged matter. Saturn's North Pole hosts a persistent hexagonal cloud pattern. This six-sided structure remains stable over long periods, shaped by atmospheric flow and rotation. Similar patterns can form in rotating fluids under the right conditions, showing how simple motion can create striking order. Saturn's atmosphere contains bands and storms similar to Jupiter's, but with softer contrasts. Ammonia clouds and deeper layers interact, producing subtle shifts rather than constant upheaval. Saturn's weather is active, yet restrained, moving in long, graceful patterns. Uranus is unusual among the giant planets for having very little detectable internal heat compared with Neptune and Jupiter. Why its internal heat output is so low is not fully understood. It may relate to how heat is transported within the planet or how it was stored during formation. Uranus keeps some of its energy hidden. Neptune, by contrast, releases a significant amount of internal heat. This energy drives strong atmospheric circulation, feeding storms that can appear and disappear over years. Neptune's climate is shaped as much from within as from the faint sunlight it receives. Neptune's moon Triton has a thin atmosphere that expands and contracts with the seasons. As sunlight warms its surface, nitrogen ice sublimates into gas, then freezes again as conditions change. Triton's atmosphere is temporary, responding directly to distant warmth. Pluto and Charon are tidally locked to each other. Each keeps the same face toward the other as they orbit. This mutual locking creates a stable configuration where day and night patterns remain fixed relative to their partner. Beyond Pluto, some Kuiper Belt objects are contact binaries, formed when two lobes gently merged. Their shapes reflect slow collisions rather than violent impacts. These objects preserve the delicate conditions of early formation. Long-period comets originating from distant reservoirs may take thousands or millions of years to complete an orbit. Their paths stretch far beyond the familiar planets, carrying them into deep space before returning briefly to the inner regions. When comets approach the Sun, volatile ices sublimate, releasing gas and dust. This process creates a surrounding coma that glows faintly in sunlight. The coma can grow larger than planets, even as the solid nucleus remains small. The tails of comets separate into dust and ion components. Dust curves gently along the comet's path, while ion tails stream straight outward, shaped by the solar wind. Together, they trace invisible forces acting across space. The solar system's age is estimated by studying meteorites, which preserve early materials. Radioactive decay within these rocks provides clocks that point to a formation time of about 4.5 billion years ago. Some meteorites contain tiny grains older than the solar system itself. These pre-solar grains formed around other stars and survived the collapse of the solar nebula. They are microscopic travelers from before the Sun existed. The Moon's surface preserves a record of early bombardment. With little erosion or tectonic activity, impact craters remain visible for billions of years. The lunar landscape acts as a historical archive, keeping time through scars. The Moon influences Earth's rotation, gradually slowing it. As energy is transferred through tides, Earth's day lengthens by tiny amounts over vast periods. Time itself stretches subtly in response to gravity. Solar eclipses are possible because the Moon and Sun appear nearly the same size in Earth's sky. This alignment is temporary in cosmic terms, shaped by distances that are slowly changing. Some moons in the outer solar system may host hydrothermal vents on their ocean floors. Where water meets warm rock, chemical energy can be released. On Earth, such environments support life without sunlight, suggesting similar possibilities elsewhere. Europa's ocean may interact with its rocky mantle, allowing chemical exchange. This interaction could provide energy sources that sustain long-term activity beneath the ice. Ganymede's magnetic field creates its own miniature magnetosphere within Jupiter's larger one. This layered interaction forms complex auroral patterns, shaped by overlapping fields. Callisto's lack of strong tidal heating has allowed it to remain relatively unchanged. Its ancient surface preserves impacts from early eras, offering contrast to more active moons. Saturn's rings contain gaps created by orbital resonances. Where a moon's gravity tugs repeatedly at ring particles, clear divisions form. Order emerges from repetition rather than force. Some small moons embedded within rings accumulate material over time. As they orbit, they sweep up nearby particles, slowly growing and shaping their surroundings. The solar system's planets follow predictable paths, yet their long-term stability depends on delicate balances. Small gravitational interactions accumulate slowly, altering orbits over millions of years. Despite this, the system remains remarkably ordered. Chaos is limited, constrained by shared motion and distance. In this steady arrangement, nothing needs to hurry. Each world continues its pattern, shaped by forces that act patiently, without sound, across spans of time too long to feel directly. The solar system endures not because it is rigid, but because it is flexible, adjusting quietly while keeping its overall form. Motion persists, gravity remains, and the gentle mechanics of space continue, untroubled and constant. Far from the familiar paths of the major planets, time stretches in different ways. Objects move more slowly, sunlight grows faint, and change becomes subtle rather than dramatic. Yet even here, physics continues its quiet work, shaping worlds that rarely announce themselves. Haumea, a dwarf planet in the Kuiper Belt, spins so rapidly that it is stretched into an elongated shape. Its rotation is fast enough to overcome gravity's attempt to pull it into a sphere, creating a form more like a flattened oval than a globe. This unusual shape reveals how balance between spin and gravity can sculpt a body without violence, simply through persistence. Haumea is also surrounded by a ring system, making it one of the smallest known objects to host rings. The particles orbit in a narrow band, likely formed from debris left by a collision long ago. Even at great distances from the Sun, rings can form and remain stable, held together by the same rules that govern Saturn's more famous display. Makemake, another dwarf planet beyond Neptune, reflects an unusually large amount of sunlight. Its bright surface is thought to be coated in frozen methane and other ices that scatter light efficiently. This reflective shell keeps Makemake cold and luminous, a small, distant world that quietly shines against the dark. Eris, one of the most massive dwarf planets known, follows an orbit that takes it far from the Sun for most of its long year. At its most distant point, sunlight is extremely weak and surface temperatures plunge. Eris spends centuries in deep cold, moving slowly through space with little change, preserving ancient ices at its surface. Chariklo, a centaur object that orbits between Saturn and Uranus, also possesses rings. This discovery showed that ring systems are not limited to planets or dwarf planets. Even relatively small bodies can maintain delicate structures if conditions allow. Chariklo's rings are narrow and dark, subtle reminders that complexity does not require size. Centaurs themselves are transitional objects, moving on unstable orbits that cross the paths of giant planets. Many are thought to originate in the Kuiper Belt before being scattered inward. Their lifetimes in these regions are limited, making them temporary visitors rather than permanent residents. Some centaurs display comet-like activity, releasing gas and dust despite being far from the Sun. This behavior suggests that volatile materials can be triggered by processes other than direct heating, such as crystallization of ices or internal pressure changes. Activity does not always require warmth, only imbalance. Comet nuclei are often described as dirty snowballs, but their structure is more complex. They are mixtures of ice, dust, and organic compounds loosely bound together. Their low density indicates a porous interior, allowing gases to escape easily when warmed. These fragile bodies survive by staying cold and distant for most of their existence. As comets lose material with each close pass to the Sun, their surfaces change. Jets can carve pits and cliffs, reshaping the nucleus over time. Eventually, repeated passages can exhaust the volatile supply, leaving behind a dormant object that resembles an asteroid. Comets can age into stillness. Some meteor showers on Earth occur when our planet passes through debris left by comets. Tiny particles enter the atmosphere and burn up, creating streaks of light. These events are predictable, repeating each year as Earth intersects the same orbital paths. Even brief flashes in the sky are connected to long-lived orbits. Earth's atmosphere itself slowly leaks into space. Light gases such as hydrogen can reach speeds that allow them to escape Earth's gravity. This process is gradual and ongoing, balanced by replenishment from other sources. Atmospheres are not sealed containers, but dynamic systems with soft boundaries. Mars lost much of its atmosphere over time, partly because it lacks a strong global magnetic field. Without magnetic shielding, solar wind stripped away lighter gases more efficiently. The planet's reduced gravity also made retention more difficult. Mars did not suddenly change, it thinned, slowly, until conditions shifted. Venus shows signs of atmospheric escape as well. Ultraviolet light breaks apart water molecules high in the atmosphere, allowing hydrogen to drift away into space. Over long periods, this process contributed to the planet's loss of water. The surface we see today reflects the accumulation of countless small losses. Mercury's weak magnetic field is offset from the planet's center. This asymmetry affects how solar wind interacts with its surface, allowing charged particles to strike directly in some regions. Mercury's magnetosphere is fragile and uneven, offering limited protection against the Sun's influence. Jupiter's gravity acts as both shield and disruptor. It can deflect comets away from the inner solar system, but it can also redirect objects inward. Its immense mass reshapes trajectories across vast distances. Jupiter does not simply sit in its orbit, it rearranges space around it. The Galilean moons are locked in an orbital resonance. For every orbit Ganymede completes, Europa completes 2 and Io completes 4. This rhythmic interaction maintains tidal heating, especially for Io and Europa. Their internal energy is sustained not by isolation, but by shared motion. Saturn's moon Iapetus has a stark, two-toned appearance. One hemisphere is dark, absorbing sunlight, while the other is bright and icy. This contrast affects temperature and ice migration, reinforcing the difference over time. A simple imbalance becomes self-sustaining. Iapetus also features a massive equatorial ridge that runs nearly around the Moon. Its origin remains uncertain, with ideas including remnants of an ancient ring or internal processes. The ridge stands as a quiet anomaly, a feature without a single agreed explanation. Uranus's moons orbit in alignment with its tilted equator, following the planet's unusual orientation. Their paths reflect Uranus's past, likely shaped by a massive collision that tipped the planet on its side. Moons remember the events that formed them. Miranda, one of Uranus's moons, displays extreme geological variation. Its surface is marked by cliffs, ridges, and regions that look patched together. This suggests a history of disruption and reassembly, possibly from tidal forces or impacts that reshaped it internally. Neptune's moon Proteus is irregular and dark, reflecting very little sunlight. Its shape suggests it never became large enough for gravity to smooth it into a sphere. Proteus, likely formed from debris after Triton's capture, disrupted Neptune's original satellite system. The capture of Triton likely released enormous energy. As Triton's orbit settled, tidal heating may have melted interior ice and driven geological activity. Neptune's moon system bears the imprint of that violent rearrangement. Pluto's surface also shows layers of haze particles that settle from its atmosphere. Sunlight triggers chemical reactions high above, producing complex molecules that drift downward. These hazes tint Pluto's landscape with subtle color. Charon's surface bears deep canyons and fractures, indicating internal expansion or freezing of a former ocean. As water froze, it may have expanded, cracking the crust. Charon's quiet exterior hides signs of past transformation. Some Kuiper Belt objects are highly reflective due to fresh ice exposed by collisions. Over time, radiation darkens surfaces, but impacts can reset this process. Brightness becomes a marker of relative youth at the surface. The solar system contains dust produced by collisions between asteroids and comets. This dust forms a faint cloud known as the zodiacal light, visible from Earth under dark skies. It glows softly, scattering sunlight along the plane of the planets. Interplanetary dust slowly spirals inward toward the Sun due to radiation pressure and drag. The process is gentle but relentless. Even microscopic particles follow predictable paths shaped by light itself. The Sun will not remain unchanged forever. Over billions of years, it will exhaust hydrogen in its core and begin to evolve. Long before that, its gradual brightening will affect planetary climates. Stellar life cycles unfold slowly, yet they guide the future. Stars like the Sun end their lives as white dwarfs. After shedding outer layers, the remaining core cools over immense spans of time. This fate awaits the Sun, though far beyond any human timescale. Planetary systems elsewhere in the galaxy show a wide range of configurations. Some contain massive planets close to their stars, others host compact systems with tightly packed worlds. Our solar system represents one outcome among many. The solar system's relative calm may be due in part to Jupiter and Saturn's early migration. Their movement through the young disk shaped the distribution of material, influencing planet formation. Early motion set long-term stability. Resonances between planets can amplify or dampen orbital changes. These interactions are subtle, unfolding over millions of years. Stability is not static. It is maintained through constant adjustment. The asteroid belt never formed a planet because Jupiter's gravity disrupted accretion. Repeated perturbations prevented material from settling into a single body. What remains is a scattered archive of early building blocks. Some asteroids are remnants of differentiated bodies that were later shattered. Their fragments carry pieces of former cores or mantles. Meteorites sometimes reveal this internal history. Carbonaceous asteroids contain organic molecules and water-bearing minerals. These materials may have contributed to Earth's early inventory of volatiles. Impacts were not only destructive, they were also deliveries. Earth's oceans may owe part of their existence to such early bombardment. Water arrived from multiple sources, accumulated gradually, and remained because conditions allowed it. Habitability emerged from convergence, not a single event. The Moon stabilizes Earth's axial tilt, reducing extreme variations over time. This stability supports long-term climate consistency. A single companion influences planetary behavior far beyond tides. Mars's axial tilt varies more dramatically than Earth's over long periods. These variations contribute to climate changes, redistributing ice and altering surface conditions. Without a large stabilizing moon, Mars's orientation is more flexible. Jupiter's Trojan asteroids orbit near stable points ahead of and behind the planet. These groups share Jupiter's path without colliding. They represent a population trapped in gravitational balance. Some Trojan asteroids may have originated far from Jupiter, captured during planetary migration. Their composition preserves clues about early solar system dynamics. Saturn also hosts Trojan moons, smaller companions, that share orbits with larger moons. These configurations demonstrate how stability can exist, even in shared paths. Planetary rings are shaped by the Roche limit, the distance within which tidal forces prevent material from forming a moon. Inside this boundary, rings persist. Beyond it, moons can grow. Over time, moons can migrate outward due to tidal interactions. As they move, they alter resonances and ring structures. Motion reshapes relationships continually. Even now, the solar system is not finished. Small changes accumulate, collisions occur, and energy flows. Nothing is frozen in a final state. Across this vast arrangement, patience is the dominant force. Processes unfold without urgency, guided by gravity, energy, and time. The solar system does not rush toward an ending. It continues, quietly adjusting, carrying its long history forward, one slow moment at a time. Across the entire solar system, there is a point that does not belong to any single world. This point is called the barycenter, the shared center of mass around which bodies orbit one another. In the case of the Sun and the planets, this barycenter often lies just outside the Sun's surface, especially because of Jupiter's influence. The Sun itself moves in a small, steady wobble, responding to the gravity of its companions. Even the largest object does not remain perfectly still. Earth is the densest planet in the solar system. Its combination of a large iron core and compact rocky mantle packs more mass into each unit of volume than any other planet. This density plays a role in generating Earth's magnetic field and maintaining its strong gravity relative to its size. Beneath familiar landscapes lies a structure that is heavy, layered, and quietly powerful. Saturn's atmosphere produces lightning far more energetic than storms on Earth. These electrical discharges occur deep within its clouds, driven by rising and sinking material in a hydrogen-rich environment. The flashes are rare to observe, but when detected, they reveal that even gentle-looking cloud bands can host intense internal motion. Jupiter's moons, Io, Europa, and Ganymede, influence one another through tidal resonance, but they also subtly affect Jupiter itself. Their combined gravitational pull shapes currents in the planet's magnetosphere, linking moon and planet in an ongoing exchange. Motion is never one-directional. Influence flows both ways. The Sun's light pressure exerts a measurable force on small particles. This radiation pressure can alter the paths of dust grains and shape the tails of comets. Light is not only illumination, it is momentum, gently pushing matter across space. The solar system contains regions where gravitational forces balance precisely, known as Lagrange points. At these locations, objects can remain relatively stable with minimal energy use. Spacecraft and asteroids alike can linger there, suspended by the geometry of motion rather than anchored to a surface. Earth's orbit is only mildly elliptical, helping keep the yearly change in distance from the Sun relatively small. This gentle eccentricity helps keep seasonal energy differences moderate over the course of a year. Stability here comes not from perfection, but from balance within a narrow range. Mars's thin atmosphere allows sound to travel differently than on Earth. Pressure waves move slowly and fade quickly, meaning a Martian breeze would sound faint and subdued. The physics of air changes when air itself is scarce. Venus's clouds contain droplets of sulfuric acid, formed through chemical reactions driven by sunlight. These clouds reflect much of the incoming light, contributing to the planet's brightness in the sky while also trapping heat below. Appearance and effect move in opposite directions. The solar system's inner rocky planets formed from materials that could withstand higher temperatures. Metals and silicates remained solid close to the young Sun, while lighter compounds were pushed outward. Composition followed temperature gradients, leaving a lasting imprint. Jupiter emits powerful radio waves generated by interactions between its magnetic field and charged particles. These emissions can be detected from Earth with radio telescopes, allowing scientists to listen to planetary activity across space. Uranus's atmosphere shows subtle banding that becomes more apparent during certain seasons. As sunlight returns to previously dark regions, atmospheric circulation changes, revealing patterns that were hidden during long winters. Neptune's storms can appear suddenly and disappear just as quietly. Dark vortices form, drift, and fade over years, leaving little trace behind. Even violent motion can be temporary. Pluto's orbit is tilted relative to the plane of the planets. This inclination carries it above and below the main disk of the solar system, giving it a path that feels detached, yet still bound. The Oort Cloud, if disturbed by a passing star, can send comets inward long after the encounter itself has passed. Events in the galaxy echo slowly, delayed by distance and time. The solar system is surrounded by a faint background glow created by scattered sunlight reflecting off dust. This glow shifts with viewing angle and season, a subtle reminder that space is never completely empty. Over billions of years, planetary surfaces darken under constant exposure to radiation and micrometeoroid impacts. Space weathers everything, slowly changing colors and textures without erasing form. The solar system's long-term stability arises from spacing. Planets are far enough apart to avoid frequent disruption, allowing their orbits to remain predictable. Distance itself becomes a form of protection. Every object here, from the sun to the smallest grain of dust, follows the same underlying laws. Gravity, motion, and energy apply without exception. Complexity emerges not from different rules, but from their patient repetition. Nothing in the solar system is truly isolated. Fields overlap. Orbits interact. Light travels, pressure pushes, and mass responds. Each part contributes quietly to the whole, whether noticed or not. And so this slow arrangement continues. Worlds turn, paths curve, heat flows outward, and cold waits beyond. The solar system does not announce itself. It simply persists, steady and vast, carrying its long story forward in silence. Good night.